Hello everyone, welcome back to grade 12 University Physics. This is Unit 4, Lesson 6. We're going to talk about how to actually make E&M radiation, all the different types, right? So when we say electromagnetic radiation, we mean the way in which electric fields and magnetic fields sort of oscillate and cause each other to happen via Maxwell's equations. So we know that light's an EM wave, right? We've talked about light as a wave, sort of having wave-like behavior in terms of dispersion and diffraction and refraction, all that sort of stuff, right? So we have to expand this a little bit as well, because all electromagnetic radiation behaves like light. So we have radio waves, which are in the sort of, meter all the way up to, like, kilometer type wavelengths. So we're talking very, very long wavelengths, up to all the way up to gamma rays that have wavelengths that are smaller than atoms. We're talking about subatomic atom type wavelengths. And this is all part of what we call the electromagnetic radiation, the electromagnetic spectrum. Sorry. So we take our wave, and however the wave is, whatever the wavelength is, sorry, that defines where it is on this spectrum. Our eyes are tuned to this very small band between 400 and 700 nanometers. Okay, that's what we can see. That's what the cones, yeah, sorry, the cones in our eyeballs. The cones are the color ones. The rods are this is in our retina. Our retinas have these cells that are called the rods and cones just by their shape, and they detect light in this 400 to 700 nanometer range. But that doesn't mean there isn't, other light. We can call all of this light. But when we say the word light, we mean visible light. So, how do we make this stuff? So, remember, Maxwell's equations, they sort of define how electric fields and magnetic fields are produced, and we put them together and we come up with what we call, a wave equation. And in that wave equation, hiding in there, is the speed of light. So if I start moving a charge, if I take a charge and I move it up and down, that's going to produce an electromagnetic wave. If I move the let's say, take a wire. A wire is some sort of conductor, and it's made of a metal, which means that there's electrons allowed to move freely throughout the whole thing. And I take those electrons and I move them up and down at a frequency, let's say at a couple hertz. Whatever frequency I move that electron up and down at, that's going to produce an electromagnetic wave at the same frequency. So if I want to produce faster frequencies, I just have to oscillate, or put an electric current through that wire, going up and down, oscillating at that same frequency. This is how we produce radio waves. This is how a radio works. Radio is basically just a wire, a long wire typically, and there's an oscillating current going into that wire, and as it oscillates, it produces an electric field around it, and that electric field produces a magnetic field that produces electric field that produces electromagnetic radiation, a wave at that frequency. Let's see, let's go to a little, this is a PhET simulation. Now, unfortunately, this is an older simulation. It uses flash, so it had to sort of convert itself into a non-flash thing, so it doesn't work perfectly. But if I play it, let's see if this works. Oh, it's a bit choppy, but that's just having to do with how flash is implemented in this. So this electron here in this wire is going up and down, and that's a changing electric field, right? So there's an there's a current that's changing with respect to time, that's producing an electric field that's changing with respect to time, which then will produce a magnetic field by Faraday's law. And then that will produce a changing magnetic field at that same frequency, and then back and forth and back and forth, and we get this wave produced. That's what this red line is showing. This is this wave that's going up and down, it's oscillating at the same speed at which the electron is oscillating. it's traveling at the speed of light, and it can go over to a uh, a detector here. So this is the transmitter station, and this is your radio in your house. Um, the antenna is just basically a wire, and those waves are going to push the electrons up and down, and that's a signal, and that signal can be processed by a radio and turned into a radio. That's just how your radio works. These are called radio waves because they have this long wavelength. So we're like radio stations are in the megahertz. So the electrons are going up and down a million times a second, hundreds of millions of times a second. Okay, and that's producing these long wavelengths. All right, you can use the wave equation to calculate what these wavelengths will be. If you look on your radio dial, find your favorite radio station. You know the frequency. You know F. We know the speed of light is 3 times 10 to the 8 meters per second. So we divide those numbers, and we can come up with the wavelength, right? Because lambda is equal to c divided by f. And we can find that wavelength as something in the order of meters. Okay, so this is how radio waves are transmitted by, are produced by moving these electrons up and down. So that's one way we can do that. What about microwaves? So let's increase the frequency a little bit more. Now we're going to talk about again megahertz. So we're going to be pushing that frequency up, reducing the wavelength down into the nanometer scale. So basically, what a microwave does is it uses the way that in which magnetic fields interact with electric fields. So basically, what happens is we have an anode and a cathode. Sorry, there's the anode here. This is this copper, this red part. We have this copper with these holes in it. Weird. And there's these, the cathode in the middle. Cathode anode, that's just the positive and negative. Cathode is positive and the anode is negative. So we have that, and we put a high voltage, some 5,000 volts between the two, and that's going to produce electrons that are going to fly towards here. Now, so that's the first thing we do. We use a high voltage to produce electrons. So these electrons are going to come off of this metal and will get launched towards this anode, right, by the electric potential there. Then we're going to produce a magnetic field in these little cavities, these holes. And that cavity, the shape of that cavity, the radius here, this hole, actually chooses an electron. It chooses the rate in which the electron spins. Okay, so we're going to centripetally accelerate electrons, and we're going to make them go around, and we're going to pick frequencies. Once they start spinning around and around and around, these electrons moving around, they actually produce electromagnetic radiation, which is at the same frequency in which they spin around in these circles. Okay, so the geometry of this anode, this is called a magnetron. The geometries inside here pick the 2.45 megahertz. Okay. Oh, sorry, I apologize. That should be gigahertz. A little typo there. So that's 2.45 gigahertz. Now, what's important about that frequency is that's the same frequency in which water molecules want to vibrate at. Okay, so it's a sympathetic vibration in which the microwaves that are, well, we'll go to there. So we basically generate this frequency in here. We generate this frequency of E&M radiation in here. Then it's connected to a coupling loop that then sends it out via a waveguide to, it's basically a little metal box that lets the waves bounce through it, and it goes into the microwave. And then when those microwaves hit your food, it actually takes the water molecules and starts vibrating at this certain frequency, which is the frequency in which water wants to vibrate at. And increasing the vibration in the water causes the food to warm up. So basically, we're picking the right frequency that water wants to vibrate at. And vibrating the water heats up your food. Okay, so microwaves in this case are produced by this magnetron that is just basically a frequency picker. via these cavities. Okay, so microwaves now, again, this is in the order of a tenth of a nanometer up to 10 nanometers. Okay, and you can calculate the wavelength of your microwave. It's something like 16 centimeters or so, I think. You guys can do that calculation yourself. Interesting, you can actually, there's a video of, if you go know the Electro Boom YouTuber, he actually uses a microwave to calculate the speed of light by finding hotspots on your on some food or on a box. I think he uses. I think he puts a cardboard box in a microwave, finds the hotspots, finds the distance between the hotspots, and multiplies by the frequency, right? Because c, right, the speed of light is equal to f lambda. So I think this was like 16 centimeters or so, and then the frequency we know is 2.45 gigahertz, and that'll actually give you the speed of light. I wouldn't do it. Just I watched the video. Don't put cardboard boxes in microwaves. Don't play with microwaves. They're kind of scary. Okay. What's the nice thing about microwave is, if you notice, there's a metal screen in front of the window, right? A metal screen with tiny little holes, and that works as a shield. That's what we call a Faraday cage that stops the microwaves from getting out. Because the size of the holes are big enough that they don't allow the microwaves to get through. Because the size of the microwave, the wavelength, sorry, is in the order of like 16 centimeters or so. Those holes are millimeter size, so they can't get out. They're too large for the holes, and then we can have a piece of glass in front of it and we can see through it. Okay, so they are completely safe. You can stand in front of a microwave, you can put your face in front of a microwave, because that metal screen in front of there acts as a Faraday cage that stops the magnetic microwaves from coming out. Okay, all right, now, well, this is a fun one. Infrared. So infrared light. So infrared light is sort of longer, just on the other side of red. So if you just go a little bit longer wavelengths than red, so 700 nanometers is the farthest we can see. If we go a little bit farther than that, we get in the orders of tens of nanometers. We call that infrared, and we produce this usually through the vibrations and rotations of atoms, the atomic vibrations. Okay? Instead of electrons being oscillated, right? Instead of us taking electrons and making them go at certain frequencies, we're going to actually take the atoms themselves, the bonds between the atoms, and we're going to cause them to vibrate. So here, this is the vibrational modes of water, right? These are the hydrogen atoms, these are the oxygen atoms, and they can vibrate. They get longer and shorter. They can do that symmetrically or asymmetrically, or the whole thing can start bending back and forth, or the whole thing can actually vibrate, coming towards us, rotating a little bit, or the whole thing rotating. These are three different modes in which it can vibrate. Here, this is a different one. This is like a, I don't know, what is it, carbon tetrafluoride or something like that. And you have all these different modes. And each of these different modes, these different ways in which they vibrate, corresponds to a different frequency. And those frequencies are much higher, in the order of, this sort of wavelength. So these things will vibrate at very, very high frequencies, 10 to the negative 14 hertz, something like that. And they produce light as they do that, because they are clouds of electrons. And the clouds of remember, this atom itself is a bunch of electrons. Well, hydrogen, for example, is just a still electron, but then it's bound to this other electron in this oxygen. So we have this covalent bond. So it's basically these clouds of electrons, and they're vibrating. So when these clouds of electrons vibrate, they produce infrared light, because they're charges that are moving in time. They're oscillating charges oscillating clouds of electrons. And I say clouds because of quantum mechanics. We'll get to that in lesson 5. But imagine there's these electrons that are there in this around this hydrogen atom, and they're vibrating. As they move these frequencies in which they want to, they generate electromagnetic radiation. We call this infrared. Now, the temperature in which they vibrate, so the higher the temperature of the material is, we get more and more molecular vibrations. Right? The higher the temperature something is, the more kinetic energy is available internally. Now, that's what temperature is. Temperature is the average kinetic energy internally of a material. How much energy there's actually stored inside in the vibrations of the molecules. Okay. So the higher the temperature, the more energy there is, and the more energetic these vibrations can be. And we end up with what we call a black body radiation. Now, this is these curves here. And as you can see, there's as things, let's just go to a different simulation here. I'll show you what I mean. So if we have something that's cold, let's say, Earth temperature, 200 Kelvin. So that's like, let's go 250 Kelvin. That'd be like room temperature here. Now, we don't see any light here. If we zoom right in, oh, there it is. We can see that we have, in the order here, this is very long wavelengths. Each of these are one. So this is micrometers. This is like 15 micrometer wavelength. So very, very low. We can't see this at all. This is up here. We would see them. But once we start warming up, I'm going to zoom out. Once you start warming up, once we get things hotter in the order of, let's say, it's like 1,000 Kelvin. It's like 700 degrees. Let's go to your oven temperature. Oven's 750. Okay, so we start getting more intensity, and this curve starts to get pushed closer and closer towards our visible light. And once things get even hotter, see, now we're starting to get a little bit of red. When things start to heat up, so these are 900 degrees Celsius, an object, like if you say some metal, we get it hot, it starts to glow. And it starts glowing off at a deep red. And then once we start going even hotter and hotter, the peak of this, what we call a Boltzmann curve, this shape here is called a Boltzmann distribution, named after Ludwig Boltzmann. It gets pushed closer and closer into we have this tail here, this left-handed tail that gets farther and farther into visible. So we're starting to get more and more yellowy. Right, so here we're now into 2000 Kelvin. A light bulb is about, that's the temperature in which the tungsten filament in your light bulb is about 3000 Kelvin. And as you can see, we're starting to get, let's zoom in on the visible here. We're starting to get more and more. It's mostly still in the red. They're still mostly red, but we're even starting to get some blue in here. So we start getting further and further into this visible spectrum until we start actually getting yellow. Okay, we started getting yellow, and then even once we get to sun temperature, outdoor temperature is about 5,600, 700 or so, we get a white color. Even that's a bit bluish. See, this is the color. You may recognize this color from white balance on a camera. White balance is measured in Kelvin because it's the peak of it's the color produced in our black body radiation. So when we have 7,000 or so, it's very, very blue because we've pushed our distribution farther and farther into the blue part of the spectrum. Once we get down to colder temperatures, it's mostly in the reds. Okay, so this is how white balance depends on temperature. Okay, and then once we get even hotter, super 10,000, we are now in the ultraviolet type color. So we can via molecular vibrations and super hot things, we can actually get in the order of we can get things uh, producing electromagnetic radiation in the blue, this ultraviolet part of the spectrum. But typically, since our sun is around 6,000, that's our white typically. Okay, this is our typical white, and it's the Boltzmann distribution produced by something that's 5,000 degrees Kelvin. Okay, so you can see as things are cold, they produce red light, and the hotter they get, the bluer the light they produce. All right, and that's these Boltzmann curves. Now, the shape of this curve is actually very important, and it's not really important for us in Unit 4, but it's very important in Unit 5, and we'll return to this shape. So keep that thing in mind. The fact that this curve drops and doesn't just continually go up forever, physicists couldn't explain it, and it caused some serious problems and led to what we call the quantum revolution, our understanding of physics from a quantum mechanical point of view. All right, so that's infrared. Visible light we can produce mostly through atomic excitations. And what we mean by that is by bouncing electrons that exist in our atoms around the different orbitals. So let's say here, let's say hydrogen here. It has an electron, and it's what we call the ground state. This is the electron orbital in which it just exists in normally. If we excite this hydrogen atom, we get it excited somehow, but fire electrons at it, put some light at the right frequency at it, heat it up even sometimes, it's able to bounce to a higher energy state. So we provide some energy to it, it's going to jump to this higher energy state. Now that's an unstable energy state, so it's going to drop back down. But when it drops back down, it's going to produce a photon of light. And that photon of light actually has energy that's exactly equal to the amount of energy, just because of conservation of energy, whatever the difference between the energy levels of these orbitals are, that's going to be the energy that's produced in this photon. I'm just going to use that little gamma to represent a photon. And a lot of the time, this is in the visible spectrum. Here's some what we call discharge tubes. These are when we take a gas that's a helium, neon, argon, krypton, xenon. We take these gases and we put 5,000 volts across it. So there's going to be 5,000 volt electrons being launched from the anode to the cathode, and it's going to get these tubes squeezed down, and it's going to hit a bunch of these atoms in here, and they're going to excite them, and then the atoms will jump up to the electrons will jump to a certain higher energy state and then come back down. Put all those different energy states together, we produce these colors that have distinct spectrum for distinct atoms. Our fluorescent lights work in this manner. Our fluorescent lights have mercury in them, and that mercury is excited by electrons, just the exact same way as these tubes, but there's mercury in them. And so we have a potential across some electrodes. Some electrons get fired across the tube, excite the mercury in the tube. Then the mercury releases that energy across a certain spectrum, and then the inside of the tube is coated with some fluorescent material that picks up the UV light that the mercury produces and gives it off at the nice white light that we like. Okay, so our fluorescent lights use this way. Okay, that's how we use our those long tube lights that you use in the schools or in your basement or something like that. Fluorescent lights work by atomic excitation. Sorry, electron excitations. So we're taking those electrons and we're bouncing them across different energy states. This looks very similar to your Bohr diagrams that you use in grade 9, and it works in the exact same way. Those empty shells, like let's say hydrogen, right? Hydrogen we draw usually in our Bohr diagram from grade 9. We have one electron here. And if you might make helium, we'd have a second electron. But really, those other shells that are empty are just like little shelves that can, those rings, they can actually hold electrons, but they don't hold them all the time. They only hold them when we excite them. We get up to different energy levels, and they'll give off different wavelengths of light. We'll talk about this again in our Unit 5. You'll also talk about this in chemistry when you talk about quantum chemistry. I think 4U chemistry has it. I think so. Okay. All right. What about X-rays? Now, X-rays are even farther. So now if we do atomic excitations, but from very, very high energy levels, from like the 5th or 6th or 7th energy level, that's a huge amount of energy that's released, and it produces very, very high-powered light, high-frequency light. And these are called X-rays. One second. Now, the easiest way to do that is you take electrons and you fire them at metals. Metals have they have lots and lots of electrons in them. They're free to move around, so it's a lot easier to get electrons in metals to jump up to higher energy states. So you take some metal and you fire high energy electrons at it. It's going to bounce some of the electrons up to way high energy states and then drop them back down at equally high energies. Well, it's not going to drop. It's going to drop down to the ground state, but release very high energy light, which is called an X-ray. Basically, in a tube, it looks like this. This is a very old X-ray tube. Basically, these are the anodes and the cathodes, and you're going to fire the electrons at this piece of metal, and then the electrons are heading out this way. And once it bounces off this angled piece of metal, it's going to produce X-rays. So it's going to produce a beam of X-rays in this direction, and they're just very, very high energy light. This is what a modern X-ray tube looks like in an X-ray machine. Again, these are the anode and cathode. It's going to fire electrons at this spinning piece of metal, and it's going to generate high energy X-rays. Okay? And it's going to produce a nice stream of X-rays for us. And those X-rays pass through tissues at different amounts, and the more of them are absorbed by your bones. So X-rays allow us to see our bones as opposed to our skin. You can basically see through your body through an X-ray. Okay? They used to have these things in schools, these nice Crookes tubes. Unfortunately, they're pretty unsafe, right? You can get cancer from these X-rays. These high energy photons like this can go into your body and manipulate your DNA. Basically, that's why they're dangerous. They can take your DNA and just slightly change a couple nucleotide base pairs here and there, and next thing you know, your cells start doing strange things. Okay, so kind of dangerous. Now, last one we're going to talk about are gamma rays. Now, this is when we go even farther. They can have very similar energies to X-rays, but we're now talking about a very different way of producing light. This is really cool. So X-rays are when we push atomic excitations to the highest levels. So we're taking electrons and bouncing them around an atom still. If you take a nucleus can actually have nuclear excitations. And in the same way in which electrons have energy states, a nucleus also has energy states. And we can actually have nucleons, so protons and neutrons, bouncing around inside the nucleus to produce light. So just like we have electrons that can move around, the nucleus itself has, in this what we call our shell model of the nucleus, has different energy levels. And then as the nucleons bounce around inside our nucleus, they can actually produce what we call gamma rays. Gamma rays are nuclear excitations. Okay, these are the shells that live inside our nucleus, according to what we call our magic numbers. I'll put a link into the description of what these things are. This is really cool stuff. This is nuclear physics. How very similar to the 2, 8, what is it, 2, 8, 18 type numbers that you had to memorize for doing Bohr-Rutherford diagrams. Nucleons have very, very similar states in which they exist in. The protons and neutrons inside the nucleus at 10 to the negative 15 meters. And they can bounce around inside there and produce gamma rays when they go to higher or lower excitation states. This happens a lot in radiation. When we talk about nuclear radiation, there's three main types: alpha, beta, and gamma. Alpha is when a helium nucleus is emitted. So that's what is that? That's He2 4. So that's 2 protons and 2 neutrons are given off, and the charge is plus. Or you can have beta decay, where we have an electron that's given off, or sometimes a positron, depends if it's beta minus or beta positive decay. And then we can also have gamma radiation, which is gamma decay, which is a gamma ray being produced, which is light. So gamma radiation typically happens when we have nucleons, so the nucleus, basically just energy levels jumping around. And a lot of the times it happens along with other decays. So gamma radiation is produced along with alpha and beta, since sometimes the nucleuses that are produced are in a higher energy state and then have to drop down and giving off these gamma rays. So let's look at an example here. So cobalt-60. Cobalt-60 decays via beta minus decay. So it goes from cobalt, which is 27. One of the neutrons inside cobalt changes to a proton and it becomes nickel. Okay, so this nickel gives this new excited nickel state. So the nucleons in there have to rearrange themselves from this excited state into a lower energy state. And when it does that, it gives off 2 gamma rays. And these are the energies of the 1.2 and 1.2 and 1.3 mega electron volts. That's a way that we can measure energy from this higher state of nickel. Okay, so sometimes it gives off, see, this is at 98%, 99 so this tells us almost 100% of the energy that's given off, the decays that happen. So this is cobalt. Let's slow down here. Cobalt is 2760. So that's 27 protons and what would that be? 33 neutrons, making a total of 60 nucleons altogether. It has a half-life here of 5.3 years. So it will decay. So if I have a kilogram of it, in 5.3 years, I'll have 500 grams. That's what that's telling us. In another, 10.6 years, I'll have 250 grams. So every 5 years, half of the stuff is gone. So most of it gives off a electron. This is what this beta minus means. That means there's an electron given off. That energy of that electron is 0.31 meg electron volts. That's the electron that leaves. Okay, at 0.31 meg electron volts. Now, then, almost instantaneously, because it's at a high energy state, it has to drop down. And it drops down actually twice. And it gives off 2 different, so there's one gamma given off, and there's a gamma given off. And there is a very, very small chance that it decays to this lower energy state, and only 1 will be given off. But almost all the time it'll give off 2. And there'll be 1.2 mega electron volt, and then 1.3 mega electron volts. Okay, so that's how cobalt decays via beta minus radiation. Another example here is lead. So lead goes from lead 210 to lead 206. Right, so we're going from here to here. So a sort of radioactive lead to a not radioactive lead. And it does that through what we call a decay chain. This is the decay chain of lead from 210 to 206. It becomes bismuth by either, most of the time it goes to a higher energy state bismuth, but then it drops down and gives off some gamma radiation. So it gives off an electron here, then it'll give off a gamma ray. Then it'll give off another electron here as it becomes polonium. Notice this is going from 82, 83 to 84. So this direction, we're adding protons. Okay, we're converting neutrons into protons. So we're going from lead to bismuth to polonium. And then we're going to lose those protons again by giving off an alpha particle. which is a helium nucleus. Not neon, helium. That's a helium nucleus, 2+. Okay, and then it goes to lead. So the important one that I want to talk about here is this guy here. So basically, it gives off a 15 kiloelectron volt electron here. But because it's in the high energy state, when the nucleons rearrange themselves to a lower energy state, it has to give off that energy somehow. And it gives off that energy through a gamma ray, right? Because conservation of energy, it has to go to a lower state, so it gives it off. These numbers here are the half-life, 22 years, 5 days. Bismuth-210 only lasts for 5 days. Polonium-210 has 138 days, and then it goes to this lead-206, which is stable for the most part. Almost all decay chains end in lead because of its stability. Okay? So there's a quick little decay chain that shows how we produce gamma radiation. So again, these are where the nucleus itself is in a higher energy state. It has to drop down to a lower energy state, and when it does that, by conservation of energy, it has to give off the energy as electromagnetic radiation, and we call that a gamma ray. Very high energy, in the same order as X-rays. Can even go farther though. These are the super high energy. Last thing I want to talk about gamma rays are the mystery of gamma ray bursts. So using X-ray observatories, we've been able to see some of these incredibly energetic events in space. We're talking like the most high energy events that exist in the universe, basically. We're talking about all of the energy that our sun would produce in its lifetime of 10 billion years, produced in microseconds. So these are these gamma ray bursts. They're produced by some huge event. We don't know exactly. Possibly a supernova, possibly black holes colliding with each other. We don't know. It's one of these astronomical mysteries. We see these high intensity pulse of gamma radiation from somewhere in space, and we're still trying to figure out exactly what happens to them. But there are these huge events, and here this is a picture of all these different ones that have happened. This is over 5 years. Using a gamma ray space telescope, it shows us all of these events. This middle band here, that's our solar system, not solar system. That's our galaxy. That's the Milky Way, producing all this gamma ray. This is like the background gamma radiation. But we care about all these little blops everywhere. These little lights that are these incredibly high-powered things that just happen. We don't know why. Okay, so just quick summary. So we have radio waves that are produced by oscillating currents. Microwaves are when you take a high frequency oscillating current. Infrareds are when the molecules themselves are vibrating. We make light when we excite the electrons inside the atom. When we can have multiple, we can hugely high energy atomic excitations produce X-rays. And then when we take the nucleus itself and start manipulating nucleons, we can have gamma rays being produced. Okay, so there's a quick little 40-minute video on how to make light in all the different frequencies, all the spectra across the electromagnetic spectrum. All right, so no homework for this one. Just memorize all your different types of light and how to make them. All right, so that's the end of Unit 4, and next we're going to move on to the fun stuff, the relativity and quantum mechanics and modern physics. We're going to push the envelope of physics. All right, well, I'll be talking to you. Take care, guys.